Hello and welcome back to Calculus 1. We are starting chapter 5 to dig deeper into the halls of integration. Anyway, yeah, I've been preparing that sentence for the last 17 hours. We are going to look into first approximating area under the curve, and then we are going to use integrals in the next section to find the exact area under the curve. So this section is really basic in the sense that we are using rectangles to approximate the area. Rectangles are easy to, area of the rectangle is easy to compute. So we will compute as many of these areas as we can. We add them all together, and that would be approximately the area. So here is the idea of the whole thing. We have some kind of a function, and then we cut the space x0, x1, x2, x3, x4, these values on the x-axis, and that gives us a partition. So that's a partition on the x-axis, where the x0, the first one, and x4, in this case, the last one, are our a and b. We are looking to approximate area under f of x on interval a to b. So here's what I'm going to do. I'm going to label these rectangles 1, 2, 3, and 4. Well, they're not rectangle yet. What I'm going to do is I'm going to go to each one of these, and from the left corner draw a rectangle. So I completed these rectangles. We can see that delta x is x1 minus x0, also x2 minus x1, also x3 minus x2, also x4 minus x3. So delta x is always the difference between these. But we can also see that we have 4 rectangles, so delta x is easier computed if you go minus a over 4. I gotta write everything from scratch now. So delta x is b minus a over 4 in this case. So if you look at any of these rectangles, you have the height, which is f of x0 for the first one, times delta x. So the overall area is going to be approximated by sum of all other areas. So this over here is read as sum of all areas. All right, here we go with the constant crashing. So it's not update related because there are no new updates. Area is approximated by the summation of all areas, so that's AN, and this is read as sum of all areas. I'll start. I guess the internet is acting up. But I see that the string quality is poor as well. So I have A1, which is the first area, and that's going to be the height of the rectangle, which is function computed at x0 times delta x. So height times the width. So that's area 1. Area 2 is f of x1 times delta x. Area 3, f of x2 times delta x. And area 4, f of x3 times delta x. There's a network lag over there. I see it. So now, sum of all areas is going to be A1 plus A2 plus A3 plus A4. So our area is approximately equal to f of x0 dx plus f of x1 dx plus f of x2 dx plus f of x3. Dx, we can factor out dx. And just get these function values. I'm going to call this left-hand sum. This is with 4 rectangles. Actually, this one. And the reason why it was called left-hand sum is because if you look at your picture, it was the left corner of each partition which gave birth to the rectangle, okay? If you use the right-hand corners, it will be the blue ones, going the other way. Now, we also observe that there is a significant amount of error here. Everything over here colored in red is error. And there's a lot of it. So the actual true area is, I would say, significantly smaller than what we are going to compute. Because all of this is error. All of it. So can we do better? And the answer is yes, by increasing the amount of rectangles. If you have more rectangles, the error immediately decreases. And if you will see later, if we use infinitely many rectangles, you are actually getting the exact area. Good luck computing infinitely many rectangles, right? You gotta sit there forever and still not get there. So if I am to draw the same picture, cut in half, and cut in half, and now cut each one of these in half, you can see that by using the left we are eliminating a lot of error, because remember that the old one was the blue here, and all of these blue squares or rectangles, all of the blue is the error that has been eliminated because we are using more rectangles. So the finer the partition, the less error is introduced into the approximation. So more rectangles means less error. It's a trade-off, amount of computation versus the precision that you need. Now, for calculators and computers, 10,000 rectangles is nothing, right? So it's easy when you have the software do the work for you. Clearly, you don't want to do 10,000 rectangles, right? Calculation with 10,000 by hand. So let's use this on the problem. Say you want to compute the area under square root of x on interval, say 1 to, what number here? 8, thank you. Couldn't remember numbers. So one to 8. Remember that you can put any amount of rectangles in there. How many do you want to put? There is an easy number that we could use. 7, right? If you put 7, every delta x is 1. Can you put 24 rectangles? Yep. Can you put 2 rectangles? And 3 and 4. You can put any amount you want. But since 1 to 8 is 7 divisions, I am going to put 7 rectangles. It's going to be annoying to compute, but I would say such is life, right? So we decided to use n equals 7. 7 rectangles. So now we can create left-hand sums, and as you can see, left-hand sums are going to undershoot the area. We're going to get less than what we need. So what do I have? Delta x is b minus a over n, which is 8 minus 1 over 7. 7 over 7 is 1. So we know that each delta x is 1. Area is approximated by, what do I have? Function computed at 1 times delta x plus function computed at 2 times delta x, function computed at 3 delta x, plus function computed at 4 delta x, plus function computed at 5 delta x, function computed at 6 delta x, plus function computed at 7 delta x, and then plus function computed at 8. No, we're not computing 8. There's no rectangle, so that 8 is the left point. Check your rectangles, you should have 7. 1, 2, 3, 4, 5, 6, 7. Good. We do have 7 rectangles. F of 8 does not have a rectangle to the right of it. so that f of 8 could be the left-hand side for. Right? If something is the left-hand side, then the rest of it is on the right. There's nothing to the right of 8. So now we plug in all the functions and everything. The function is a square root function. So I have square root of 1 times 1 plus square root of 2 times 1 plus square root of 3 times 1. And then we go all the way to 7. Obviously times 1, we don't have to worry about it. Let's go. 1 times 1 is 1 plus 1.41 plus 1.73 plus 2 plus 2.23 plus 2.3 something. .45, and then square root of 7, 2 decimals is okay, 2.65. So now we add these. I'll add the first 3, the second 2, and the last 2, and then we'll add all of those. So this is 1, 4, then a 4 there, plus 4.23 plus 5.1, and that's going to be 13.47. 13.47. So this is underestimate, right? Because there was an error, and the true area is higher than 13.47. That's that. As long as you understand that you're using a function to compute the height of the rectangle, you're using delta x, which is the width, you multiply the two, and you will get area of a single rectangle. You have to do that for each one, and then as you compute all of them, you have approximated area. You can also do the right-hand sums. So let's say your function f of x is equal to, next week, well, what function should we use now? Yeah, I love your enthusiasm. What? Beautiful. 1 over x on interval 2 to pi. That's a terrible interval. You are disqualified from giving any further input for today. Oh, maybe you said 5, and then I don't have to disqualify you. I want 6 rectangles. And I also want the right-hand sum, not the left-hand, like we did so far. So draw the picture, try to see where the stuff goes. So right-hand sum,
For the right hand, just to let f of 6 dx plus f of 5 dx plus like that way.
No, you will still start well, when you draw the picture, you will see where, and you do the delta x, you will see where they all fall. You start from left to right. Why would you start right to left?
Right hand side, just make a difference.
No, it's just from where you draw the rectangle, right? If you have a function like this, and you have two sides hitting, left-hand side will emerge from here, so that will be left-hand side, and the right-hand side will emerge from here and do that. So it's a difference in the height, but you're still using same numbers on the bottom. It's just on which height the rectangle. Good question.
Guessing doing right hand sum. Does it have to be squared because it's an area, or does it not matter if it's a graph?
You are using, well, you will say units squared, inches or something, but you don't square a function or anything. You are using 1 over x. Yep. So let's take a look at a quick graph over here. It's going to have a piece that looks like that. There's also one there, but we don't care about that one because we go from 2 to 5. And we are supposed to have 6 rectangles. So there they are. Our delta x is going to be 5 minus 2 divided by 6, which is 1/2. And then we're going to do right hand. So we have these numbers, but then we have the in-betweens, 2.5, 3.5, and 4.5 as well. So right-hand side means we go to the right and then draw the rectangle towards left. So the first number we are using is 2.5. So we have 1 over 2.5 times 1/2 plus 1 over 3 times 1/2 plus 1 over 3.5. So right hand and left hand only matters to draw the rectangle. We always go from the smallest to the largest value. 1/4 times 1/2, 1.5 times 1/2, and at the end 1 over 5 times 1/2. And all we need to do is to compute this. So that's 1/5 plus 1 over 6 plus 1 over 7 plus 1 over 8 plus 1 over 9 plus 1 over 10. And if you count this, you do have 6 areas there because there are 6 rectangles. No, because there is no rectangle for 2 in this case. Right-hand side starts with this point, which is 2.5 point. In order to have, we would have to have a rectangle on this side to start with 2, but we don't. Yes, but then they would look like this. They would be above in this case. So you just now punch all of these in the calculator. 2 decimals is a good precision. Make sure you round the 3rd decimal properly. And we're done. Do we all have 0.85? Good?
I have a question.
Yes.
From the left hand side, why is it under the not above?
I said right hand side. And you are correct. It would be above the graph if it was left. Yes. In this case. That's it. Decide how many rectangles you are going to use, or obey how many rectangles you were told to use, right, in the problem, depending on which way the problem is stated. If you want to make it, try to compute as many as you can, but not too many, so you stay forever computing this stuff. Exam usually has one of these questions, not to make it too annoying. So the next part of this lecture is to say one more time and realize that the more rectangles you have, the less error you have. If you want the exact area, you would have to you will have to get infinitely many rectangles involved. That's, in the case of math, obviously possible to do because we can have infinitely thin rectangles. So the idea now is to build up the amount of rectangles to infinity so that we can have exact area under the curve. So I'm going to draw again a larger picture here. x0, x1, x2, x3, x4. We have A and B on those endpoint ones. And what I'm going to do is write dx everywhere. And then say that the difference in between any one of these is delta x. But the difference between any two is 2 delta x. The difference between any three is 3 delta x. So x0 and x3 are 3 delta x's apart. So I can say that x2 is x1 plus delta x, because location of x1 plus add delta x to it, you get x2. x3 can be, sorry, I want to start with x0. Delete, 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 delete. x1 is x0 plus delta x. x2 is x0 plus 2 delta x. x3 is x0 plus 3 delta x. And x4 is x0 plus 4 delta x. We can conclude from here that xi is always x0 plus I delta x, and this I is counter. Location and how many delta x's. So xi. We also know that x0 is A. So we have now a formula that xi is equal to A plus I delta x. Whoa, what happened with the air conditioning? It shut off. It's not negative 37 degrees yet. I can still feel all my fingers. Why is this off? So we can find location anywhere with this. Now, why would I want this? Well, think about this. We know, you should look at the screen, and then I will, you can write it later. Because I'm going to build this, write and talk at the same time. It's important for you to see it. Look how you build the infinite rectangles here. You say, I'm going to take the heights and multiply those by delta x. You know that's the area of a rectangle, right? You have the height and the width. So here's what's happening. I'm going to take and add all of the rectangles So we know this summation means add all. The rectangles will start going from 1 to some value n. So if that n is 5 rectangles, you had 5 rectangles to add. If that n is 6, you had 6. If it's 10,000, you had 10,000. So this n for our previous problems was either 4 or 7 or 6, depending on which problem we had before, right? So here's the crucial part. This is still a finite number of rectangles. The major part is in front. You send the number of rectangles to infinity. And this is known as the Riemann sum. Riemann is a German mathematician who figured out integration, figured out area under the curve, and made it possible for our physics and engineering and everything else to develop through accumulations and so on. So we can talk about energy, we can talk about mass, we can talk about many aspects of physics that are developed today to give us technology and stuff that we have. So this is where it starts. This is what it's known as the quotation mark limit definition of integrals. Okay, this is equal to integral a to b f of x dx, and this is what finds the exact area under the curve. It is extremely useful concept. It does a lot of great stuff. What is the integral? Integral is the infinite sum of rectangles. That's what it is. It's accumulation. So derivatives measure the change, and you are chasing the slope of the tangent line. Integrals are dealing with area under the curve, and they measure accumulation, summation, putting stuff on a pile. All right, that's what it does. So when you're looking at this formula, one more time, you first have, I'll erase this, you first have f of xi times delta x, which gives you a rectangle. Then you add all the rectangles together, and then you send the number of those to infinity. It's a very simple concept to put together. To compute stuff, however, not so simple. But before we hit the calculations for that, I just want to briefly describe this summation notation. So sum, sigma. So if you have sigma of, let's just do sigma of I, counter I, where I goes from 1 to 6. This means 1 plus 2 plus 3 plus 4 plus 5 plus 6. That's all it is. Because you're adding values. The counter here will pick up values from here and add to the next one, and it will stop when it reaches 6 in this case. You can also have summation of, let's say, I squared. Let's say I goes from 2 to 5. Simple. 2 squared plus 3 squared plus 4 squared plus 5 squared. You can have summation of 2 to the I, where I goes from 0 to 3. What is this? 2 to 0. Very good. So you just have to be careful where is I. I is the one that is going to change 1, 2, 3, 4, 5, 6, 7. Or, in this case, with 2, so you have to be careful where it starts, where it ends. We can introduce x and functions. You can have, let's say, I goes from 1 to 3 of just, let's say, xi. So what's happening here? What should I write? Very good. 1x plus 2x plus 3x. Awesome. Because I will pick up values 1, 2, 3. You have 3 terms. What is the summation of I starts at 1, goes to let's say 3, and we have x to the I. Yep. So we just need to trace where the I is and then keep repeating picking up the next value for I every time. Computer science, hey, that's where you begin. All right. So now what do I have to figure out the exact area? I have a formula for delta x, which was b minus a over n. I have a formula to figure out where each location of xi is by using a plus I delta x. And we finally have that the area, exact area, is equal to the limit n goes to infinity, summation 1 to n f of xi times delta x. These are the formulas that we use to set up and solve the integral, to solve the exact area. Now obviously later on you're going to use the shortcut. This is the limit definition, right? This is the long way of doing the problem. What's going to happen next class? We're going to use the short way on how to do this. And after that, after your exam, well, you will just use software to get it anyway, right? So where do we begin? Let's use, let's find area under 2x squared minus 3. F of x. Find the area under the curve on the interval, I don't know, 10 to 12. You know what? I can use 0 to, I'll change this. But I'll put plus 3. So plus 3, area is question mark on interval 0 to 3. All right. There's a lot of steps to consider here, a lot of calculations. So let's start. The first order of business is to figure out what delta x is. We do not say n is 6, n is, right? We're going to use eventually infinitely many. So we're just going to leave it as n. So our delta x is 3 minus 0 over n, which is 3 over n. So delta x is 3 over n. We're going to use that result. Gotta be able to find it. The next part is to locate every single x that we have in this problem, which is the other formula. So xi is a, in this case we know that a is 0, plus I times delta x, which is 3 over n. So these xi's are 3i over n. This I is a counter, it's not imaginary. It has nothing to do with imaginary numbers here. The next part, you want to make sure stream is going. The next part for us is to create f of xi by plugging in xi into the function and working it out. So f of xi is equal to 2 times 3i over n squared plus 3, and now crank this algebra. we have 18i squared over n squared plus 3. That's our f of xi. So you have to get all of these guys on the pile, and then you can finally put the problem together and then solve the limit. So now area is equal to the limit n goes to infinity, summation 1 to n, and now inside over here I have to take the function, which is 18i squared over n squared plus 3, and multiply that by delta x. Delta x was 3 over n. So that was the setup. We had to find delta x, xi, plug xi into the function, obtain the function, and then we have function and dx to delta x to plug into the limit. And all we need to do now is to solve this. That's it. Just this. So the first order of business is to distribute 3n to both. So limit n goes to infinity, summation 1 over n, and we have 18 times 3, which is 54, I squared, over n cubed plus 9 over n. Don't forget parentheses or brackets, because summation has to apply to all of these terms. All right, now the next order of business is to separate this into two sums. One that operates on these the first term, and the one that operates on the second term. So limit n goes to infinity, and now in parentheses I have a summation 1 over n of 54i squared over n cubed plus summation of 9 over n, again 1 to n for summation. Limit applies to both, so I have to put the parentheses there. Now, something that we did 5,000 times, if the variables don't match, you treat them as constants. Remember that the limit for derivative, when you had that f of x plus h and so on, was h goes to 0. It was completely ignoring x's. Summation does the same thing. The variable for summation is n. Sorry, is I, because it's I equals 1, right? I equals 1. So the variable for it is I. It doesn't care about number 54. It doesn't care about n cubed. You can kick those outside, because the summation will only operate on I squared. Everything else is technically factored from each term, and then later when you solve it, it multiplies back. So limit n goes to infinity. I can kick 54 over n cubed in front and have summation I goes from 1 to n of I squared. Plus, I can do the same thing, 9 over n, and then I'll just have summation of 1. Now, this and this, there are formulas in the textbook which tell you what these guys are equal to. So we have our limit, n goes to infinity, and then I have 54 over n cubed, and then I squared is given as n plus 1, 2n plus 1 over 6, plus 9 over n, and when you have a constant, it's just going to be cn, so just times n. Parentheses closed in the wrong spot. There we go. Now 54 and 6 would cancel to 9. You can also cancel one of the n's, which is easy. So you have 9 n plus 1, 2n plus 1 divided by n squared plus just 9 on the other side. And if you take a look, the highest exponent in the numerator is n squared, right, squared, and the denominator n squared, so it's just the ratio of front coefficients. So what's the limit of the first parenthesis? Or first fraction? They have the same exponents. So it is, yes. So the exact area over here is 27. Let's do one more and then hit the break and then review. Sounds good?
You need to memorize like what the sum of all
So is this on the final or the last exam or both? Yeah.
So let's see another example of this. So one from the textbook. 4 minus x squared from negative 2 to positive 2. So f of x is 4 minus x squared from negative 2 to positive 2. Create delta x, create xc, and then
Can you also do it from 0 to 2 and then double?
yes, because it's symmetric. We don't learn those formulas in 5.3 or something like that, but yeah.
I wrote it differently.
So delta x is 4 over n. Very good. And we have our xi to be -2 plus 4i over n, right? Now we plug that into our f of x to get f of xi, which is 4 minus -2 plus 4i over n squared. And we have to FOIL all of that. So we have 4 minus, and here we have 4 minus 16i over n plus 16i squared over n squared. So f of xi is negative, oh actually wait, 4 minus 4, that cancels. So I have 16i over n minus 16i squared over n squared. Are we good on this one?
Yes.
Thank you. So all I need to do now is to plug all of this in a limit and compute. Limit, n goes to infinity, and we have the summation, I goes from 1 to n. In parentheses I have 16i over n minus 16i squared over n squared times 4 over n, which I'm going to distribute now and get 64i over n minus 64i squared over n squared. I goes from 1 to n.
N squared is n cubed. You already have.
That's what I said, yes. Thank you. Which is further limit, we split the sums and kick out constants. So kick out constant 64 over n squared, summation of I minus 64 over n cubed, summation of I squared, equal to limit n goes to infinity, and now you have a 64 over n squared, summation of I is n plus 1 over 2, over 3. So n plus 1 over 2, and then minus 64 over n cubed, n plus 1, 2n plus 1 over 6. So one of the n dies. 62 over 4 is 32. So we have the limit, n goes to infinity, 32 n plus 1 over n minus 64 over 6, we can cancel by 2, get 32, one of the n's dies, so n plus 1 over 2n plus 1 divided by 3n squared. Now if you take a look at all these n's, we have enough of them. They just all cancel, and we get, we don't need limit anymore, we're done with that. We have 32 minus 64 over 3. Those are the front coefficients, because n squared on top and squared on the bottom. And times 3 will be 96 minus 64 over 3, 32 over 3 as the area under the curve. So if you are to draw this, you will see the parabola that opens like this, and this is your negative 2 and positive 2. Function goes through this, and we have area. So all of this over here is 32 over 2 area. Sounds good? So that's 5.1. We are going to continue this next class regarding this.
Will you ever ask us to like once we learn the
well, let's just say
will you ever
bye. Hold on.